Electromagnetic
Induction.
induction. We start by asking one question. The current that you see in your household, how is it produced? How do you get this? What are your general idea regarding this? Can you tell me? What are your real general idea? How do you get this light? From where do you get it? Any idea? Any idea from where this light, this current is coming from where? How do you generate current? How do you generate current? Current
So from
is
transformers.
no. In this chapter we will learn transformer also. The function of transformers. Transformers are, they play with the voltage. They either increase the voltage or decrease the voltage. Okay. And what are the principles behind the transformer we will learn. We will also learn the concept of generator. What is the principle behind these generators? You have seen in hydropower plants, you have seen in thermal power plant that there is a big motor which rotates. When this motor rotates, it generates current. Okay. So what is that motor? What is that thing? We call that actually a generator. So electromagnetic induction and alternating current will be all regarding this. Ready? So we'll start with electromagnetic. Before we go to electromagnetic induction, we need to pay attention to Faraday's experiment. What is Faraday's experiment? Okay. So to understand Faraday's experiment, you can carry out this experiment in your house also if you have a magnet. Okay, and a very small bulb or something like that. Generally, this experiment, what you can carry out is the one which is carried out in physics lab is something like this. That we will place a, let's say this is the axis. We have a coil here. Again a coil, no current carrying coil here. This time, wait a minute. This time the coil will be this is a cylinder, maybe some kind of core, above which I am going to wrap some coil. Maybe copper coiling. Simple copper wires, nothing else, which is been wound over. This blue, it can be a paper cylinder or it can be just anything. Okay, just to make a shaft. Here is the wire which is coming out, and from that side here is the wire which is coming here. We have studied galvanometer, right? So we are going to place a galvanometer here. I'm going to place a galvanometer. Here is a galvanometer. I have shown you galvanometer earlier.
Yes, sir.
So this is the needle. I will draw separately the picture of the galvanometer, this needle here. So here is our that circular frame. there is a needle standing or pointer. Here we see lots of, here is the needle, and is written, here it is written 0, here is written 30 or so whatsoever. This is minus 30, this is plus 30. Okay, now the connection, here are the 2 points, 2 terminals. After a suitable way they are connected here. This is also from here, it is connected like this. Okay, next what else we have? We have a bar magnet. This side being north, this side being south. Okay, this is Faraday's, Michael Faraday's experiment. Michael Faraday's experiment, and what he see is that we are interested. Okay, this is his first most basic experiment. This is the first experiment, experiment 1. Okay, what he has done is that when he takes this bar magnet towards the coil, he observed deflection in the galvanometer. So first, do you understand the setup? What is the setup?
Yes, sir.
What is setup? Setup, a moving coil galvanometer. I have shown you a Western type, is connected to a coil, as shown. A bar magnet, okay, wait a minute, I need to mention here something. Coil as shown, wound over an air core. Okay, you can see the core. A bar magnet moves towards the coil. No, not towards. Bar magnet can move in and out of the coil. Observations. What are the observations? Number 1, as the magnet moves towards the coil, galvanometer shows deflection. Number 2. When the magnet moves out or moves away from the coil, there is a deflection in the galvanometer, but now in the opposite direction. Number 3. When the magnet do not move, no deflection is observed. In the galvanometer. Okay, what else did he observe? He also observed that next is when the magnet moves faster. Magnet moves faster. Deflection is also more. Let me explain you what I mean, one at a time. So, when you take the magnet close towards the coil, what is happening is that the galvanometer, the needle which is there, it moves in one particular direction. Which direction, we will see that later. Okay? I'll explain you which direction. It moves, let's say it moves in one direction, like this. So when the magnet moves towards the coil galvanometer, it shows deflection. This is what is showing the deflection. Next time when the magnet moves away from the coil, it shows deflection again. But this time the deflection is in the opposite direction. If the magnet is not moving, no deflection. Correct? The fourth point, if the magnet moves faster, closer or away, the deflection is even more. So it depends on the speed. What is happening? Now galvanometer is a device which is used to measure or detect current. So when the galvanometer is giving some deflection, it means certain amount of current is getting established in the coil. Right? What is happening? This phenomenon, that means whenever the magnet moves, a current gets established in the coil. Right? This phenomenon is called electromagnetic induction. Understand? Based on these above observations, we can make some conclusion that whenever, now if you remember what is magnetic, before I carry on to this thing, let me give you a reminder what is electric flux and what is magnetic flux. You remember electric flux? Number of electric field lines crossing and unit area perpendicularly is called electric flux. Similarly, magnetic flux will be what? The magnetic field lines crossing an area perpendicularly is called what? Magnetic flux. So actually what is happening here, this bar magnet has its own what? Magnetic field lines, right?
Yes, sir.
These magnetic field lines, don't draw in dotted one. I'm showing you by dotted. They are not dotted because they cannot be close. They are close curved. They are not. They are not break. They cannot be broken. Okay, I'm just showing you for your reference. From you see, this magnetic flux is getting linked with the coil, right? So when this magnetic flux linked with the coil is changing, a current is getting introduced in the coil. Got it? A current is getting induced in the coil. Or EMF, a voltage is getting induced in the coil. Right? Similarly, when the magnet is moving away, again the voltage is getting induced, but this time it is in the opposite direction. That's why calorimeter is giving me deflection in the opposite sense. Which direction, how is it, I will come to that very soon. Okay? So, whenever magnetic flux linked, based on this experiment, Faraday gave two laws. He said, whenever magnetic flux linked with the coil will change, an EMF will be induced in the coil. Okay? What did he say? Isn't this our first three observation says? The magnet moves towards the coil, galvanometer shows deflection. That means magnetic flux linked with the coil is changing, a current is getting induced in the coil. As simple as that. Whether the magnet is going towards it or going away from it, it is giving. Right? And when the magnet is not moving, then definitely flux is not changing.
No deflection.
No deflection. Simple. Correct?
Yes, sir.
What about the last point? The fourth point. When the magnet moves faster, deflection is also more. Right? That means what? The magnitude of this induced EMF depends on the rate of change of magnetic flux. Rate of change means time varying magnetic flux. If the flux changes over a small amount of time is more, EMF induced will be also be more. So then, based on these above observations, based on these observations, based on Faraday's law of electromagnetic induction, so before that I forgot to define electromagnetic induction. So what is electromagnetic induction? The phenomenon which I think you have learned in class 10. I'm just revising with you. The phenomenon of producing induced EMF or electromotive force or current in a coil, okay, by changing magnetic flux linked with the coil is called electromagnetic induction. Right? Or understand?
Yes, sir.
Electromagnetic induction. So, based on above observations, above experimental observation, Faraday concluded, based on observations, Faraday gave the laws of electromagnetic induction. Laws of electromagnetic induction. What is it?
Whenever
First one. Whenever
Magnetic flux.
Whenever there is a change in magnetic flux, linked with a coil, okay, and an EMF is induced. An EMF is induced in the coil. Called induced in the coil. We call it induced EMF. Okay. Number 2, the magnitude of this induced EMF, the magnitude of this induced EMF is directly proportional to the rate of change of magnetic flux linked with the coil. So he has written like this: E magnitude is equal to d phi by dt. I said proportional, but you see I'm writing like this. No problem, because it's taken as constant, is taken as unity. Got it? This is it. These are called the laws of electromagnetic induction. Remember, I have written magnitude. I did not write this is laws of electromagnetic induction. There is actually a minus sign, which we will see now. So any question before I proceed to the next topic? So let me ask you a few questions, if you can answer. Okay, if I change the south pole, if I rotate the bar magnet and then take it close to the coil, what will happen? If now in this case north pole is approaching towards the coil, if instead south is moving towards the coil, what will happen?
Sir, still be deflection on the opposite direction.
Very good. Right? And if it is coming out, then?
Pardon, sir?
And if it is coming out, means now you are going in, I said, now the magnet is coming out. That means the south pole is coming out from the coil. Then?
South pole is coming out from the coil.
Then what do you think?
Sir, then I think even then the deflection will be in the opposite direction, no?
Yes, from the earlier case. Okay? Right? Both of you?
Yes, sir. Yes, sir.
Now let us come to next law, direction. Let us talk about directions now. What will be the direction of the induced EMF? Direction of induced EMF. Direction of induced EMF is given by Lenz's law. Lenz's law. Now what is Lenz's law? The direction of induced EMF is as such that what? Direction of induced EMF is as such that it opposes the cause producing it. Let us understand. That is, E will be minus d phi by dt. Here comes the direction, minus. Negative sign implies that. Negative sign implies that. So now this is our law for induced EMF. Okay? Now look at here. Let us look at this. Let us look at that experiment once again. I'll give you a coil here, a single one coil. Before I proceed, let's look at this coil first. If the coil in the current, you know that coil has a two faces, one top and the bottom face, right? Now you must know that the current in the coil is in the clockwise direction, means the face which you are looking will be south. And if you look at the coil such that the current in the coil is in the anti-clockwise direction, then it is that face of the coil is north pole. Okay? So let's look at the case. Let's look at this diagram now. I give you a coil. This coil is now connected to same galvanometer. Wait, I have to give some space. I am showing you the galvanometer like this way. Connected to a galvanometer. Fine. Here is the axis. This is the bar magnet. This side being north, this side being south. Let's say this bar magnet is going towards the coil. Now you please tell me what will be the direction of current in the coil. In which sense? Clockwise sense or anti-clockwise sense? So the Lenz's law says the direction of induced EMF is as such that it opposes the cause producing it. So which face is coming this side? North pole is coming toward. So in order to prevent the cause, what is the cause? The motion of the bar magnet is the cause. To prevent the motion of the bar magnet, this face, the one which the bar magnet is facing, should be north pole. So as it is a north pole, that means the direction of current should be like this.
Anti-clockwise.
Anti-clockwise. Understood?
Yes, sir. Yes, sir.
So it's a very important concept out here, okay? And again we will use different law to understand this, but right now this is the most easiest one. Let us do few more questions to understand this, so that our concept get more and more clear. I'll keep this is a plane. I'll just drawing this surface to make you understand that this is a plane, and I draw a circle here. This is a coil, right? And this is a bar magnet which is falling freely. South pole is approaching towards the coil, means it will go through it. It will go to pass through it. Can you give me the direction of the coil current in the direction of current in the coil. Which side?
Yes, sir. Yes.
Clockwise or anti-clockwise?
So clockwise.
That means write an S there.
Yes, sir. That's sir.
Write an S. That's it. Clockwise.
Okay.
Finish. Right? Is prevent the cause producing it. Understood?
Yes, sir.
Just a minute. Okay, so this is how we find the direction. What about the magnitude? How will you determine the magnitude? Okay, we'll come to that. We'll come to that once again. Before that, one more. I'll check your work. Imagine this is a triangle coil. A triangular coil, and this is connected to a string suspended. Okay, we place a do you understand the situation?
Two bar magnets.
Two bar magnets are present there, like this, and it is oscillating. It is oscillating like this. Give me the direction. I'll tell you the direction of the magnetic field is like this is south pole, this side is north pole. Okay, so these are the point A, B, C. Tell me what will be the direction of current in the coil when it is coming from A to C.
A to C.
Yes.
So on the C phase, means from the north side
So
of the magnet, this will go anti-clockwise, and from the south side will go clockwise.
very good. So in this case, it is what? It will prevent coming in. Prevent coming in. What will be the direction of the coil when it crosses C, going from C to B?
C to B. C to B. From the north side will be anti-clockwise.
No. Lenz's law says it is prevent the cause producing it. So when it is coming from A to C, the coil will try not to go towards C, right? As a result, it will try to repel north-north and south-south. So as a result, its direction will be which way? This side will be north, right? So like this, simple. But when it is going towards from C to B, then it will want the coil not to go, right? So current direction will change now. Current direction will change. Now it will be in the opposite direction, because north should attract now. That means this should be now south pole, and that should be now north pole. As a result, it will try to come back. So note, direction of current or the EMF voltage switches Here is the fundamental of alternating current or alternating voltage. Right now, when this is alternating like this, it is producing an alternating voltage, sine wave or cos wave. If the pendulum is released from C, okay, it will produce a sine function wave, and if it is released from B or A, it will be a cos function. Understand? To represent that induced EMF. Gradually we will come to all this. So this is how we do electromagnetic. This is about electromagnetic induction and Lenz's law. Let us find out the magnitude. How do you find out the magnitude? May I clean it?
Yes, sir. Sorry. Finish
Okay.
writing.
An easy one first, because I will need to teach you what is magnetic flux, then we will come back to some other problem. Let us take an easy question. Magnetic flux linked with a coil changes from 2 into 10 to the power minus 2 Weber to 2.8 into 10 to the power minus 2 Weber. What is Weber? Weber is the SI unit of magnetic flux. Okay, I will discuss this. In 4 seconds, find the magnitude of induced EMF in the coil. Can you? It's a simple question. So E would be, we know d phi by dt is the differential form, but that is actually delta phi by delta t, or phi 2 minus phi 1 by t2 minus t1. So phi 2 is how much? 2.8 10 to the power minus 4 2 into 2 minus 2 into 10 to the power minus 2 divided by how much second? 4 minus 2. So that gives me how much? 0.8 into 10 to the power minus 2 by 2. So 4. So 0.4 into 10 to the power minus 2. What is the unit of E? It's an EMF. Electromotive force. Not a force, but an induced voltage. Unit is volt. E is volt. Okay?
Yes, sir.
One more question. If the flux changes from 1.8 into 10 to the power minus 4 Weber to 2.2 into 10 to the power minus 4 Weber. Okay, not 2.2. Let us do like this. Let us boost this. Let us give it a more. Let us give me to look at it. What I am doing now. I am giving a large change to 3.6 into 10 to the power minus 4 Weber in 2 seconds. In 2 seconds, find induced EMF. I'm just writing like this. Find direction and magnitude. Give me the direction also. Don't give me the mod. Find E. What do you think? Answer? E equals to how much?
Sir, delta phi by delta t. So
Which one is the final here?
pardon, sir?
Which one is final?
Sir, 3.6.
3.6 into 10 to the power minus 1.
Okay,
10 to the
3.6 into 10 to the
minus
power
1.1.
minus 4 minus 1.8 into 10 to the power
Minus 4.
minus 4 divided by 2.
divided.
I've already said 2 seconds. So 2 minus 0. So how much is the answer?
So 1.8 into 10 to the power minus.
So that gives me
So the first
0.9. 0.9 into 10 to the power minus 4 volt. So notice, if the change is large, time is short, voltage will be more. If I keep this as 2, let's say, these things are 2, let's say, how much is the difference now? 0.4 or the volt? How much is it now? 0.9.
Yes, sir.
Isn't this what we have discussed? The rate of change of magnetic flux is more, current induced will be
And
more. Second law of Faraday's law of electromagnetic induction, the magnitude of induced EMF depends on the rate of change of magnetic flux linked with the coil. So flux changes more, EMF will be more. Okay? Okay, we will stop here.